In this video, we'll learn about the reaction quotient Q, and we'll use ICE tables to determine equilibrium concentrations. Now, we've learned about the equilibrium constant, or K, which is always where you're going in a reaction. It's a destination point. Always, no matter where you're starting, the system will proceed until concentrations satisfy this equilibrium constant. Now, the reaction quotient Q is just a matter of where you are in a chemical process. Now, if Q is equal to K, then the system is at equilibrium. If Q is greater than K, you have too many products over too few reactants, and the system will therefore have to go leftward to decrease the amount of products and increase the reactants until we've satisfied that equaling K and the system reaches equilibrium. If Q is less than K, then you know that the system will continue to go towards equilibrium by shifting rightwards. You have too few products over too many reactants, so you'll build up the products and decrease the reactants en route to reaching a value where Q is equal to K. Once we've established the direction that we need to go to reach equilibrium, we will use what's called an icebox, which stands for initial change equilibrium, to determine equilibrium concentrations. So let's take this problem here, where gaseous HI is placed in a sealed flask at a certain concentration and heated to a temperature for which we know the equilibrium constant. We need to determine the concentrations of HI, H2, and I2 that will be present once the system reaches equilibrium. So initially, we have to find Q, and we'll compare that to K to determine the direction that the reaction will proceed in. And Q is solved for in the same way that K is. We have Q is equal to the products over the reactants. And since there are no solids and liquids, we just use the H2 times I2 concentration divided by the square of the HI, because there's a 2 here, that's why it's squared. Now, we know that there's only HI here, so we will have 0 hydrogen and 0 iodine over some amount of HI. This gives us a Q that is equal to 0. And because Q is less than K, the system has to shift rightward, going towards equilibrium. Next, we're going to use an ICE table, and our initial concentration of HI is 0.80 molar. Our initial concentration of H2 and I2 is nothing for both. And the system will change, decreasing the reactants and increasing the products, so we lose some amount on the left and gain on the right. Now, for every 1 hydrogen and 1 iodine that are produced, we need to consume 2 HIs, and that 2 comes from this stoichiometric coefficient. And so our equilibrium concentration of HI is just going to be 0.80 minus 2x, and our equilibrium concentrations of H2 and I2 are both x. We don't know exactly how far this reaction needs to go, and that's why we're using these variables x. So step 3 is we have to solve for x. Now we know that at equilibrium, we're going to have the equilibrium constant is equal to some amount x, that is the hydrogen concentration, some amount x, that's the iodine concentration, and that will be divided by the HI concentration, which is 0.80 minus x quantity squared. And that is equal to this 0.016, the K at this temperature that the reaction's at. Now, this, of course, simplifies to 0.016 is equal to x squared over another square. And so this allows us to take the square root of both sides. And this comes out to 0.126 being equal to x over 0.80 minus x. And if we do a little bit of math magic, we get to x is equal to 0.090 molar. As you might imagine, these problems could be a lot more complicated depending on what you really get. In this case, we could simply take the square root of both sides. In other cases, you might find that you need to use a quadratic or a cubic even. In this class, don't worry about it. Even in AP chemistry, you will not have to worry about ever solving a quadratic. So if we know that x is 0.090, that's a molarity, that is the concentration of H2. So we know our equilibrium concentration of H2. It's also the concentration at equilibrium of I2. And for the HI at equilibrium, all we need to do is subtract the 2 times 0.090 that we knew to be x from the 0.80, and we get 0.62 molar. And so there are 3 equilibrium concentrations, and they do satisfy the equilibrium expression. So that is all for this video. I hope it's been helpful. Feel free to leave any questions or comments in the comment section below, and thanks for watching.